All right, so intro to binary exploitation part 2, modern day, 90. So the 90s are over this time. So you all know who I am. I'm a third-year CS guy. I run the CTF team, and as a hobby, I do Linux VR. And if you want to hit me up on Discord, there it is. So a little quick recap from last week. Binary exploitation is basically the art of finding bugs in software and just exploiting them for whatever purpose you want. And it requires like knowledge of assembly and some C++ and C internals. And what we did last week is that we found out that you can actually overflow variables located on the stack, obviously providing that you have the ability to, and that ability comes with the programmer doing some very poor checking. And to succeed in binary exploitation, it just requires continuous exposure and learning. And over time, you will gain that methodology to succeed. So do practice chals, read some blogs, and of course, be curious, right? So probably one of the more infamous types of bugs are format strings. So functions like printf have a format string to define like how you're formatting text. Usually that's like the first parameter. And there's like a huge collection of format specifiers that you can find and how to use them, manipulate them, do pretty much any kind of text formatting you want. You can happily Google that. You'll get a huge library for that. Now, here's a question. In this snippet right here, is this actually legal, right? Is C or is Clang or GCC going to give us any warnings or errors? Or will the sanitizers like ASAN and UBSAN actually give us anything? What does the audience say? Hands up if you think it's gonna, if the compiler is gonna actually give a shit. No? So I guess all you think that it's gonna let it compile? Well, if it is legal and GCC Clang will accept it, you will get a small warning, but a lot of people disable it. And why it's a warning that it is a vulnerability, because through that bug right there on line 4, you can get arbitrary read and writes of any memory address located on like in the process space on the system. So the types of interesting format strings that you can use is %x. That specifier prints like hex values, it prints values on the stack or any kind of value as hex. And it's very commonly used in that example below on the bottom right to leak addresses, or actually not addresses, values on the stack. And %n is a very useful one because it's really fucking weird. Because it writes the number of bytes that are written to a file descriptor like standard out into an address specified for %n. So if I print like 5 characters to the standard out, it'll actually write the value 5 into some variable that I specify with %x or %n. I have zero clue why that's needed. I don't even think there's a legitimate purpose for this besides exploitation. Like legitimately, like why does this exist? And of course, everyone's favorite %p, which actually dereferences the address that you're specifying, and it's used for printing strings normally. So now we go on to ROP, and ROP is basically a method of taking over when you have the ability to use the to override the instruction pointer. You can actually use existing code in the binary to run whatever kind of program you want to. So, and wait, so yeah, and it's very powerful though on x86 and the 64-bit version because of that feature of variable length instructions. So like every instruction doesn't follow like the same length. And because of that, it allows tools like ROP gadget or wrapper to find like little gadgets or assembly snippets to use that we can like use to help us program our VM or our process. And you can see on the right that we have an example of an output from Wrapper, which is a very nice ROP gadget tool written in Rust. Cole, I think you're a fan of that. Yeah. So one key one key element about ROP that will help us, that actually gives us the ability to construct this chain, is that at the end of every like ROP gadget you see on the right side, they all end in ret. So what is ret and what does it do? So it's just a normal x86 and 64-bit instruction. So what it does is it pops the save return instruction pointer from the stack, and it places it into the instruction pointer register, and it increments a stack pointer. So that chain allows us to, like that set of instructions allows us to, when we have like a series of instructions on the stack, we can kind of like chain and just go one after the other. It gives us like a nice stream to like program, right? It's a continuous chain. So how do you use this? An example exploit that I used when I was making the solve script for Dice CTF, a challenge that I made. We can see right here we have in payload, well, ignoring the P64 because that's just encoding in the 64-bit NDNS. RDI is in this example, is a Python variable that points to an address that has, as you see right here, pop RDI. So that's what RDI would point to. And the +1 is just has it so that we go to a ret instruction, because I needed padding in that example. But you see that we have a P64 RDI. So when the binary tries to execute pop RDI, it'll actually take this, the libc like string value and then put that in the RDI register. And the reason why that when we're continuing execution after we're popping RDI is because the pop instruction increments the stack pointer again. And then ret also does that. So when that happens, we'll essentially skip over that like entry from that, which is the NSH string, and then jump over to the address that represents system on that libc binary. So quick thing about heap exploitation, it's very complex. Like this is another beast of its own that I could honestly give another talk, because there's just frankly so much stuff that you could do. But heap generally is just dynamic memory allocation. If you've taken programming 2, you've definitely used heap. And if you haven't in programming 2, I question how. But yeah, when you're doing C code, it's basically the 2 functions you'll be using are like malloc and free. And often you'll have a vulnerability in the heap that can allow attackers to get like a very strong primitive, like arbitrary read and write, or if you're lucky enough, you can even get a shell. Now, heap though is more systemic because you're actually you're trying to poke holes in the functionality of like a well-tested like program. And in this case, it's the algorithms in the C library, right? Some famous ones are DL malloc, which was an old one for libc. I think that was phased out in like 2012. Now it's like PT malloc. And if you're doing like harder targets like Chrome, they just ignore libc entirely and just run their own algorithm, which is a little like what? But the 2 common bugs that you'll see in heap are heap buffer overflows. Same idea as stack. They don't do any balance checking on your writes, so you can just override like heap metadata that allow you to do like interesting attacks. And then there's use after freeze, where if you call the free function on a pointer that you've allocated from malloc, but you try to use that same pointer again, that's undefined, like in C. It'll let you do it, but no one knows what's going to happen. But you can use that to exploit your program, depending on how that function pointer is being used, like by the program. And a great example of that is from Exploit Education, specifically their Phoenix series, specifically under heap 2. But like I said previously, heap exploitation is all about manipulating the rules set by the algorithm. Now, for mitigations, and this is primarily the reason why the 90s are over, because the industry wised up and now they're fighting back. So the first mitigation that you will always see is it's not like 2012, is ASLR. Basically, if you have like shared libraries that your program requests, like libc or like anything else, like other like shared libraries that you're loading in, they will always be randomly placed in the memory map. You can, and there's no way to like turn that off like in the binary itself. That's a system-wide level form, like variable set. But you can defeat that using format string bugs or some other info leak to leak those addresses, and doing some offset math. You can find out where like everything in libc is, or any other shared library. There's also PI, which is an acronym for position independent executable. It's just ASLR, but for the executable itself. So your life is slightly harder, especially when you're debugging, because when you're debugging, the addresses you see in Ninja or Ghidra, they don't line up to reality. Now, NX stands for no execute, and basically means that you can't execute anything on the stack. Now, to bypass that, you would use ROP. And the reason why ROP works here is because we're technically not executing code on the stack, because we're actually, when we have ROP, we're actually dereferencing those addresses, going to existing memory that has those instructions, and that memory is set for execute because that's actual code. And the two more famous mitigations are RELRO, or read-only relocation, which is essentially write protection for what's called the global offset table, which is something you'll see for dynamically linked binaries, aka something that's not static. Partial RELRO means that like the programming linkage table or the program linkage table is still writable, so you can do some like cool malicious tricks there. Full RELRO, on the other hand, yeah, both the PLT and the GOT are read-only, but that doesn't mean that it's completely useless, because you can still use that to leak addresses and thus do a nice return to libc attacker easily. Now, stack canary is a random value that's placed before the saved instruction pointer on the stack. And you can again use format string bugs to leak it, or you can do something really cool if you're lucky enough to land on 32-bit, so that you can brute force it. If the program that you're trying to exploit calls fork, because upon forking the process, the canary is still the same. So I've actually seen a chow where I think it was some Pona-owned stuff, where, because an interesting target that you could do this on is Nginx, because they call fork to handle like new HTTP requests. And you can actually brute force the canary 1 byte at a time, because the rationale here is that